Guys, today we're going to be talking about acceleration and velocity. This is good background information for those in the radiology field, especially technologists. I'm Brian Nett from howradiologyworks.com. So again, acceleration and velocity. Velocity and acceleration. So imagine you're a radiographer, you're kind of upset, you got this old cassette, doesn't work anymore, you drop that cassette on the ground, and then you kick it across the ground. So I'll draw a little cassette here, and we'll talk about it's starting at some position at time 0 when you first drop on the ground, it's starting at some position. Then it's going to slide across the ground. So at some time later, first it's starting at time t0, it starts at some position, and then tf or t final, it's going to end up at some other position. And we typically call the position, the direction of position, we typically call that x for our unit, and then maybe it went some distance d. So this is the distance that the object actually moved, and then the distance is going to be measured in units of meters, right? That's the SI unit. So we talked before about SI units. If you haven't seen that video, check that one out. And it's meters, centimeters, but typically that's the units we're going to be talking about. And then today we're more interested in how does that object move as a function of time as far as the changes in distance. So if we plot as a function of time, we make a plot as a function of time, and we plot the distance as a function of time. Imagine I was able to impart like this perfect kick, and it got up to a nice velocity, and it kept at that same velocity after some initial time. The change in distance as a function of time is what we call the velocity. And what we've drawn here is the case of a constant velocity. So the distance is changing as a function of time, just like a straight line. So if I look at the beginning and I look for some given time period, if I look at the beginning and I do, if you remember, the slope is what we call rise over run. So if I look at the beginning and I look at some given time period that we call delta t, then the delta x is how much it changed. So how far did that cassette move in that amount of time? That delta x divided by delta t. If I do the same thing later, if I do it up here, this delta x divided by this delta t would be the same thing. That means we have a constant velocity. And the other thing that we wanted to define is what we call the acceleration. So if we plot the velocity as a function of time, again, this is the position as a function of time. Where is that object actually located? And then if we plot the velocity as a function of time, so the change in position as a function of time, if we plot that, for this plot right here, we're actually talking about a constant number, right? We said the velocity is the same here as the same here. So at the beginning the velocity is the same, at the end the velocity is the same. And we're going to define the acceleration, which is the change in velocity as a function of time. And we need to define the units, right? For the velocity, the units are going to be meters is what distance is measured in, and seconds is what time is measured in, right? So then for the acceleration, it's going to be, we take that meters per second, then we have divided by time, so we need to divide by another seconds. so meters per second squared. And then the acceleration for this case, if we have a constant velocity, the change in velocity is a function of time. If we look at this velocity and this velocity, say we talk about the velocity at the very beginning, if we call that v naught, the velocity at the end, if we call v final, those two numbers are actually the same. I should have called that right here, sorry. V initial and then v final are the same. This should be t initial and t final. So v initial or v naught equals v final, and therefore the acceleration, we're actually looking at the change in velocity. So the change in velocity is just v final minus v initial divided by t final minus t initial. And since it didn't have a change, this on the top is actually just going to be 0. So this is what we call a constant acceleration. Then if we're constant acceleration, a constant acceleration means that the velocity is going to be changing constantly as a function of time. And again, we can talk about over a given range, we can talk about the average velocity. And a lot of times we'll use this little bar to mean average. The average velocity equals, again, over this range, let's say again we had t naught and t final. The average velocity, we look at on the plot, we say at t naught, where was the velocity? And that's v naught. And at t final, we say what was the velocity? And that would be v final. Then we say velocity is, the average velocity is the v final plus the v naught divided by 2. That's what the average velocity is, right? And then the change of velocity that's happening over there, or the acceleration, is v final minus v naught divided by t final minus t naught. Said we looked at the velocity being constant here, so the question is, what would the distance plot look like? And the distance plot would actually look something like this as a function of time. So in this case, the distance is changing more rapidly than the velocity because we are actually accelerating during the course of this time period. And again, the velocity at one given time point you can think of as the little parallel line to this curve here. That would be the velocity at one given time point. And just like we said over there, the velocity is just measured as, if you think about a little parallel line to that curve, the velocity right there, that what we call instantaneous velocity, or the velocity at that time point, the velocity is again just measured as the change in the position as a function of the change in time. Just the change in position over the change in time. And that's what velocity is. And then acceleration is just, again, the change in velocity given a given amount of change in time. If you're used to thinking about these triangles, we call the slope just the rise over run for the line, and that's just the change in the x position divided by the change in the time. So that, at a high level, is actually calculus. The velocity is actually the derivative of the position with respect to time, and then the acceleration is actually the derivative of the velocity with respect to time, which is the same thing as the second derivative of the position with respect to time. Again, you don't have to worry about that as a rad tech. Just worry about these basic equations, thinking about these little triangles and thinking just about the velocity is when we're talking about meters per second, and that's how quickly something's moving. And the acceleration is meters per second squared, and it's the change in how quickly something's moving. So check out our next video about potential and kinetic energy, because that also is really important as a radiographer or technologist to understand the basics of how the X-ray tube works as our electrons change their potential energy into kinetic energy.